So yeah, this is the first part of our three-part webinar today. And my name's Matt Dumont. I've got Zeb and Patrick also on here acting as support staff, so they get to sit in front of a camera and be under display for the rest of the day, which is always enjoyable. Want to give thanks to obviously Zeb, but also to Olivier and Rich and everyone else who worked on the Land and Water presentation. So back to this slide, just a reminder, if you have trouble, please consult the webinar agenda and pop questions in the Q&A as we go. There is an upvote feature, so please use that. Also, as you probably can see, this webinar is being recorded, so if you have to duck out or you've come in late, we will be posting up relevant bits out of this. Note that we're going to record the entire proceedings of today, but we're only going to publish the presentations, so any of your comments are not going to just end up on YouTube for the world to mock, ridicule, or be inspired by. Also, for those of you who are new to Google Meet, it might be worthwhile changing your layout, having to play with that. I find that sidebar is a really nice way to see presentations because it makes it bigger. But of course, feel free to play about. All right, so with that, let's crack into the goals for today and give you a bit of a guide. So we've done the tech overview and the welcome. So now you're gonna have to listen to me talk for about an hour. Hopefully it'll be at least mildly interesting. Then we'll take a bit of a break, and then we have a group assignment. You can think of this as a test, so pay attention. We will be judging. After that, there's going to be a bit of a break, at least for me. The group assignment and those discussions can kind of continue on. But then at 11:15, we're going to move into a new webinar, or at least I will move into a new webinar to talk through the Python examples. If you have no interest in Python, feel free to skip that. You don't need to suffer through it. You can just tell your bosses that the webinar went on and take a long lunch. Most of your bosses are on the call, though, so be wary of that decision. All right, so this talk, we're going to go into a bit of an intro and background, talk about lag and its importance, and then go into the discussion power as a concept and the levers that you can pull, and then we can have a couple of examples and network design and some conclusions. So, without further ado, who are we? Komanoa Solutions is a small consultancy. We work in both the research and the practice and consulting space. And our research includes, at the moment, sea level rise management under future Coast Aotearoa and some climate shock resilience. So these are extreme events and climate change. We also have a bunch of consulting streams. We've helped out with regional plans and other work for regional councils generally, but then we've also acted on the practitioner side or on the consentee side. As you can see, we're a small team, but we pack a lot of knowledge into that team. And all of us, except for Evelyn, who is our young blood, have a fair bit of council experience, so we're there. And finally, our overall mantra as a group is that everything should be made as simple as possible, but no simpler. And that's a thing that's going to keep coming back through this webinar and through the work that we do. So I want to address a potential elephant in the room, which is, we're consultants, and the goal of consultants, and by consultants, I mean consulting agencies, is to make as much money as possible and to be like Scrooge McDuck. And since that's its own thing, we seem to be doing something a little different here. We're not doing work in a way that provides the most money out of things. And so I could see why you might be suspicious. And as a council scientist, I'd be sitting here going, all right, where's the catch? When is the shoe going to drop? So I'll go ahead and drop it now. And that is that we've been on both sides of this problem, and we've seen what happens in regional planning and in limit setting. And we know that monitoring can kind of get lost in the pile. And the challenge is to come back 10, 15 years later and be in a position where we're in conflict over what the data means rather than what we should do with it. And that's something that is not fun to do, not fun to participate in, and just generally unhelpful. We've also seen consent conditions, again, from both sides of the aisle, where there are monitoring conditions, but those monitoring conditions may or may not provide the information that's needed. And so they end up in this weird space of a burden on the consent holder, but not providing value. And we just want to see that improve. And so for us, we'd rather give away this IP and allow people to work on these things and to basically be the tide that raises all the boats in terms of getting better monitoring for our environment and for our planning and for our consents. So with that, I can talk a little bit about who you all are. Before this webinar, we had a little survey to see where people were at. Now, it was only 14 people and there are 46, so we'll see whether or not this is a good sample. But by and large, people were not particularly familiar with detection power. They'd heard of it, a vague understanding, but no one responded that they felt happy to explain it. And that's a challenge. So our goal for today is to get everyone into at least that green space of happy to use it, but don't ask me to explain it, and get a bunch of you into the, I fully understand the concept, I can explain it. Let's make this part of our bread and butter. I also want you guys to know the difference between a counterfactual and a slope-based detection power and when to apply each. Understand the different levers that can apply that are part of this. Understand how lag ties into the detection power space, and then how to use it to make fit-for-purpose monitoring networks for your questions. Another piece, obviously, we've made a tool set that's available in Python. About half of the respondents to the original survey were Python users, the other half not so much. So we're aware of this, which is why we've got the webinar and this first presentation and the discussion points for everyone, and then the actual tooling for others. And the goal here is that if you're not a Python user, you're in a position where you can tell a Python user to go do the work for you and get some good results. Then briefly, a bit about the wider context. You guys are obviously familiar with the Monitoring Freshwater Improvements project underneath the Our Land and Water Framework. We were part of that project, and that's where a lot of this tooling was developed. And I'm sure that you guys have seen or have heard of these web apps that are available for rivers, lakes, and groundwaters. And these web apps do a good job of getting people to understand detection power as a concept and how to use it, but they have simplified it by assuming that lag isn't a component. And for us, this is too simple. As simple as possible, but this is too simple. And so we want to step back and think about how we can step off of that springboard and then bring in the impacts of lag and pull that together. And so that's where this presentation differs from those that you've seen. So with that in mind, let's talk about lag. I know you are all familiar with it as a concept, but I just want to read this statement out of Ascot et al. 2021. And I'll read it so that any of you making breakfast, dinner, etc., don't have to look at the screen. Despite a strong body of scientific evidence and increasing awareness among stakeholders, models and budgets used by policymakers in best management practice planning often do not adequately represent legacy end dynamics and associated time lags. Achieving this would support more realistic estimates of trajectories of change following measures to reduce end loads, managing the expectations of stakeholders, and supporting long-term sustainable agriculture. Incorporating end lags into improved models and budgets used in policy and regulatory frameworks for sustainable management of agriculture can better meet the needs of human health and the environment. And I think that's an important statement to consider. When we're doing work, we need to bring lag in and bring it in a way that captures the nuances of the problem. So specifically, what I mean by that is we all know that when we go out and grab a sample, we're not sampling one water age. This isn't a tube. At each point, we've got an age distribution. Here, this distribution is made by an exponential piston flow model, but there are various models to try and capture those distributions. And the concentration is the concentration in our receptor, in our streams or in our wells, is the age distribution times the source concentration, and the sum of that yields the receptor concentration. So moving to a spot where we just say, a lag is a certain amount of years and we're done is a bit too simple for this sort of work. So in terms of the impacts, we obviously have that lag, the step between when concentrations peak and when we see them in the receptor. But we also have the temporal dispersion, that sort of widening of the curve, the smoothing, the fact that our peak concentrations will be lower. And then we also have hysteresis. And by that, I mean where we have historical increases that are still in the post and are yet to come, those are still going to come through, and they're going to complicate our understanding of what's going on in the landscape. And just as a side point, lag is important in surface water as well. Even lags of a couple of years can have a pretty significant impact in our concentrations. Also, understanding those age distributions really can help guide where concentrations are going. So this is a plot out of a piece of work we did for Environment Canterbury. Harts Creek is a small spring-fed stream in the Selwyn Te Waihora zone, and you can see if we assume different lags in that surface water, where our concentrations could end up are radically different. And so it's important to consider that context, not only on where concentrations will go, but what that means our reductions will look like. As a case in point, I'll briefly talk through a case study in the Whakauru stream. And so this area is out near Rotorua. It's a baseflow dominated hydrology. There was a target of 0.26 milligrams a liter set from the historical measured data. And there was some intensification where forestry turned to dairy in 2008, 2009. And there are a number of age assessments on this stream. And so we have a good sense of what that age distribution looks like. So the challenge we have is that concentrations have shot way up. And you can see that here. And so when we're talking about these reductions and talking about our detection power, which we'll get to in a minute, we need to think about what's coming in that post. Where could the source concentrations be? So to solve this, and this method is implemented in the Python package, so it's available for anyone to use, we made some simplifying assumptions. We'll say, okay, we'll use a man-Kendall and a send slope to define a trend. We'll find the intercept of that trend with present or current time, that red dot, and then we'll make an assumption that concentration started at some low value here, 0.1, and then at some point they started going up in a monatomic way. And then we keep changing where that peak concentration is and what that slope looks like and where those intercepts look like until the data generally, or until the predicted nitrate values, after it's gone through that age distribution, generally looks like the concentration we're seeing. And as you can see here, it does an okay job. Obviously, it's a very simple approach, but it provides us with the ability to say, well, concentrations could be quite a bit higher. They could be up in those, 3 milligrams a liter. And if we're going to look at a 20% reduction or 1 milligram per liter reduction, that's going to be important information to know. And just to comment on this, obviously there's some uncertainty there. It's simple. That's fine for our detection power work, because all we really care about is getting in the ballpark and understanding what things might look like. Obviously, when we step into limit setting, we need to be much more precise. And so this gives me a minute for just to spend a minute and talk about a technique that we've been developing that I'm quite excited about, which is sort of taking that thought process and making it just as simple as needed. So here, this is using the data, the concentration data that we have, and our understanding of the age distribution of the water to estimate what's happening in the source zone. And so this is that same stream. You can see here, the suggestion would be that concentrations have actually, there was a steep rise and the concentrations have plateaued. Now, we can go back in time and see what things look like. So in 2015, 2017, 2019, and then 2022, and look at the information that we had. Now, this particular analysis is center seeking, which means that unless there's reasons for it to change, it won't change, which is why you see very little change coming in this 2015 example, but in 2016, 2017, we see that increase starting to happen. I think this is a useful tool that could be used in limit setting. It's much faster than building a complex regional model, and it can definitely help constrain where concentrations might go in the future. So that's my little plug. I think it's cool. I'd love to get this out in a wider project and demonstrate the usefulness. So with all that in the background, let's actually jump into detection power as a concept. So the challenge we keep running into is this: you keep using your data, and I don't think they mean what you think they mean. And that's an uncomfortable position for us to be in as regulators or as consultants. And what we want to be able to do is reject that, and reject that in a statistically significant way. So jumping into stats, for those of you who are well-versed in the space, read the comic, it's great. Otherwise, let's just talk briefly about what these values mean. So obviously, when we think about the statistical concept, we set a null hypothesis. So in the case of running a man-Kendall across your data, the null hypothesis is that there is no trend in the data. And then we set some alternative hypothesis that there is a trend. And we run the test. And the test spits out a p-value. And we can get distracted by p-values. But essentially all they're saying is, all the p-value is saying is that there is an X% chance that we have rejected the null hypothesis. We have accepted the alternate hypothesis. We've said, no, there is a trend in the data, but we've done it just by chance. The data just happened to line up in a way that it looks that way, and whoops, that was our bad. And so when we say a p-value is less than 0.5, that means that the probability of a type 1 error or a false positive, like man-Kendall detecting a slope when we didn't need it to, when it doesn't really exist, is less than 5%. And so that's our type 1 error. Our type 2 error is a false negative, where we say, there's no slope, no changes happening, concentrations aren't increasing or decreasing, but they in fact are. So with that, it's very easy to think about, okay, let's look at our data, and it's very easy to see where statistical significance comes in. The top graph here has very little scatter. We can see there's a reducing trend. We can see it visually. And so there's it has high statistical power. Middle one, not so much. The bottom one is getting tricky. So detection power then is about predicting statistical power. So to say something has a detection power is just the likelihood that your statistical power will be high enough that your p-value will be low enough that you get a significant answer. So in a very real situation, I'm monitoring a well. 20 years down the track with my monitoring, what's the probability? How likely am I to get a p-value of less than 0.5 when I run my man-Kendall or run my statistical test? And the way we do this is prediction. So in detection power, there are a number of different factors. We're going to go over each of these, so don't worry if you're not familiar with all of them. But Broadly, you've got your questions and the statistical tests you use, the noise at the sites, what's going to happen at your site, and then the things in your control, which are usually your sampling frequency and your sampling duration. So one of the questions is this slope detection. Do we observe a trend? Do we see an increasing trend or do we see a decreasing trend? This is what we normally think of, and this is what the web app is designed to look at. So the statistical tests for this are linear regression, Mann-Kendall's, and a multi-part Mann-Kendall, which I'll touch on in just a second. We're all familiar with this. It doesn't specify the size of the trend, but it's, hey, do we see a slope in the right direction? For the multi-part Mann-Kendall, this is a little bit of a side quest. It's a very useful technique that helps avoid the problem of breakpoints. So often we take an arbitrary position, what's happened in the last 10 years, run a Mann-Kendall over it, and extract some information out of that. But depending on how the data is looking, you can end up changing your results by just changing where those breakpoints set. And what a multi-part Mann-Kendall does is it doesn't assume a monotonic slope. It goes and runs a Mann-Kendall across all of the different breakpoints in your data sets, and then looks for spots where it's where it matches your expected slope, so an increasing trend and then a decreasing trend in this example on the bottom. And the Mann-Kendalls are statistically significant. And so you can see here, it does a great job of accurately describing what's going on in this data set, whereas a Mann-Kendall just cannot. So then we have question 2, and this is one that we're probably less familiar with, which is the counterfactual space. Is pathway 1 different than pathway 2? Is it more than or less? And as an example, we have here some data that's where concentrations could either rise over 10 years or fall. And can we tell those apart? Can we say that the blue pathway is bigger than the red pathway? Tests here are usually our paired t-tests or our Wilcox sign rank test. And the usefulness here is either in a prediction or a modeling space where you have one outcome, where you have a number of different outcomes that could be possible, or where you have paired catchments that are one's undergoing a trial and one's not. So with those questions in mind, let's talk about noise. And this is the other big challenge, because noise obfuscates what's happening in our data. Noise, when we think about it, there's measurement error, which is true noise. But here we need to take a slightly looser vision of it, and it just means the unexplained variance in the data. And so this is a little snippet of the Whakauru stream, and you can see, depending on how you model these concentrations, your noise can decrease. So in the top one, we just take the mean, and then it's just the raw standard deviation of the data, and you can see our noise is quite high with a standard deviation of 0.12. If we then say, oh no, we see a trend, and we fit it with a send slope and a send intercept or a linear regression, we can bring that noise down. We start modeling the seasonal components, we can bring that noise down even further. And so while noise is not fully in your control, the way that you model it can help reduce that noise and make it easier to see what's actually going on. So with noise, the next thing is sampling duration. And I like to think of this as the unhelpful silver bullet to detecting a change. If we sit there and we monitor again and again and again, year after year, eventually we will see a change, if there is one. But unfortunately, stakeholders are kind of like the kids in the back seat. They want to know, are we there yet? And when are we going to be there? And why aren't we there yet? And it can be a bit incessant. So useful to keep in mind, but not super helpful all the time. The other silver bullet we have is sampling frequency. The more we sample, the more information we'll have, and the easier it will be for us to reduce that noise, to reduce that unexplained variance. But it's an expensive silver bullet. Now, I want to touch on a subject which was raised in a comment after a previous webinar or a previous talk, where they said, you know, a higher sampling frequency might actually introduce more noise and make it more difficult to assess what's going on. So, you know, is higher frequency sampling actually the right call here? And I reject that. More data will always yield more information, but only if we do the work to make this happen. So in this particular instance, I took a true data set, this black line, and you can see it's got an increasing slope and it's got some seasonality to it. And then I resampled it. And the only error I had in resampling was that the field techs didn't go out on exactly the right day and nail, you know, the absolute peak of that concentration in our annual data. And that introduces some error. Now we can change it and say, no, we're going to go and resample in a biennial. We're going to do it twice a year. We're going to hit both the peak and the trough of that annual cycle. And you can see, yes, if we fit this with a send slope, then we've increased our error 7-fold. But if we take the time and we do the work and we fit it with that annual component, we can reduce the error by a factor of 3. So more data always yields more information, but you might have to work harder for it. And I think it's important for us to comment on why we're doing this. It's not like we've went out and had our data set, you know, our red data set here, the annual data, and said, oh yeah, that's good enough. We can tell what's going on. We know what's there. We're just going to make our lives harder. No, this is nope. The red data set did not give us the information we needed. We need more information. That means we have to work harder. So it's only adding that complexity where it's needed. And that's part of the portion of detection power, is to see where you need that complexity. Also with the pathways, there's the ratio between the noise in your site and the change that you expect. If you have a very noisy site and a very small change, it's going to be very hard to see. If you have a very noisy site and a very large change, that's much easier to see. And so that's why it's important for us to set these pathways and set where things are going so that we can actually see what changes we'd expect, how big of a change, and when can we expect that change to actually come through. So if we put it all together, this is a well in the Selwyn district, and we have some historical nitrate readings, and we can estimate a trend, and we can define the noise that's going through. So we came out to ask a question, which was, when can we detect a reducing slope? That's the slope detection power. And for that pathway, we said, all right, we're looking at a 20% reduction in concentrations off of whatever the source concentration is in this well. And then with that, we can couple it. So we've got the source, that dotted yellow line. We propagate that through to the receptor via the age distribution, and we have a future pathway. Now, in terms of the detection power analysis, we add some noise. We think about how frequently we're going to sample and how long we're going to sample, and that can give us detection power as our likelihood of getting a p-value less than 0.5 when we analyze the data. So if we exclude noise, that gray line in this bottom slope, that's our noise-free detection power. That's when we could actually see the data, period. And it makes sense, right? Before then, in 2030, we would still expect concentrations to be going up, even though they're starting to plateau. 2035, they've peaked and gone down the other side. So if we knew exactly what was going on in this receptor, we could say it then. But of course, there's noise that's going to obfuscate our ability to see what's going on. And depending on how frequently we sample, we end up waiting different amounts of time. So a typical threshold for detection power is 80%. There's an 80% chance that we'll get a p-value less than 0.5. And so we can see here in this particular example, If we were sampling weekly, great, we would see these reductions by 2040. If we decide to just sample annually, then we're probably looking out at 2060. And that is a big change and a in what we would expect. And you can see how taking the lag plus, so the lag component, that gray line, plus the detection power, or the noise component, yields our actual ability to see these results. So I just want to go back to this graph again, and you may have noticed this, that, right, of course, as our changes, as our mean resonance time, as our age distribution changes, our ability to see that detection power also changes. And one of the challenges is we end up in the space where the mean resonance time of 5, that's 12 samples a year, that detection power is a lot lower than we expect. We'd expect the detection power to be higher at a shorter mean resonance time. And what's happening here is that the change is coming through so quickly that our samples have a difficulty in adequately characterizing it, and we're not asking the right question. In this case, it would probably be better to move to a counterfactual detection power because the difference in concentration matters, but that slope is just so sudden that it's hard to detect. So with that, we can take a couple seconds break and just let everyone sort of process, rewind, drop questions in the chat if you need clarification. Zed or Patrick can always pop some information in. All right, and with that, let's jump back in. So now the big question, how do we use this? And it really is something that can apply across a wide range of things, from catchment groups, goal settings, plan changes, and consent conditions. We'll focus on those last two as some sort of worked examples. So for this, let's look at a theoretical plan to reduce the concentration in the Whakauru stream, and we'll walk through all of these components. We want to hit the concentration in the source zone of 1.5 milligrams, and we want to make that happen by 2040. And the question is, if we do this, when will we see a reducing slope? So stepping in, we'll focus in on this, on the chunk of data that has this increasing slope. We'll use that to estimate the noise, and to get a sense of, what's the trend in concentrations. We then go back to this diagram again and use that trend and that slope and that intercept to estimate the source concentration. So again, here, by having a source concentration that started increasing in about 2004 and went up to 3 milligrams a liter by 2022, that gives us about the right concentration, about the right pathway. So then we look at our forward predictions. So here we say one option, our sort of base estimate, is that concentrations stay the same. And that's that blue line as it comes up and yield and plateaus. And then the other option is we have those reductions implemented in 2022 and reducing to 1.5 milligrams by 2040. Now, that gives us this red concentration. You see, we can expect concentrations to continue increasing for about 10 years, which makes sense. It's a 12-year mean residence time. And then we can expect those concentrations to start decreasing. So we have this forward concentration pathway. We kind of know what's going on. Now we can take and add the noise component on top of it and estimate our actual detection power. So in this case, if we sample 5 years, 10 years after we implement those reductions, we don't expect to see anything. There's no way that we can see anything. When we start sampling out to 15, 20 years, we start seeing results. And here we can say, quarterly sampling is probably not good enough. Whereas when we look at the moving to monthly sampling, that's great. We can see quite a bit out of that, and we can expect to see changes with confidence in 20 years after we implement those reductions. And so this gives us a couple of things. One, we can set expectations from the get-go. We can tell community groups, hey, we won't expect to see these changes for 20 years. We might see something at 15, but probably not 20 years, setting those expectations. And that's just a fundamental challenge of the system that we have. There's nothing that we can do to change that. And it also provides us with an idea of sampling frequency. In this case, monthly sampling is necessary. It provides a lot of additional value. More frequent sampling, weekly or fortnightly, doesn't provide a lot of extra information. So that means that 12 samples a year is probably our as simple as possible, but not too simple value. To think about it in a flip side, let's talk about a theoretical consent condition. So in this case, we have a new activity which could increase groundwater concentrations. We've got 2 existing monitoring wells in the area, cleverly named near and far. And we want to look and say, all right, what's going to happen with this consent? Now, our existing data looks like this. I can tell you there's no trend because it was sampled from a random distribution with no trend. The advantage of theoretical and examples. And we can derive some estimate of the noise in the wells. The near well is a little bit noisier, and the far well is not quite as noisy, but they're all around 0.2 milligrams a liter in terms of the noise. And this is from quarterly data. The applicant has gone through and done some complex groundwater modeling, has pulled together, which incorporates not only what's happening at the source, but also what would likely happen based on the lag that those aged estimates. And they've worked out and said, okay, well, we have 2 scenarios. We have what we think is going to happen, this blue scenario, this hey, everything's okay scenario. And then we have the this is a problem scenario. And we want to ask the question, how frequently do we need to sample before we can tell that blue scenario from this red scenario? How frequently do we need to sample to be able to say these are significantly different in each of the wells? So within that, we run our detection power calculations, and we end up with these results. So here are sampling durations in years, and then our sampling frequencies. Now, in this particular case, the applicant has suggested using quarterly sampling, which is the existing quarterly sampling, so that the regulator, in this case the Shire, is doing all of that work for him. Now, that's great for them. They don't have to do any extra work. But it's not great for us as a regulator because it's not good enough. We can see that we are going to cross that threshold of being able to see whether these 2 scenarios are different for, 2.5, 3 years. If, however, we insist that they move up to monthly sampling or even fortnightly sampling in the far well, we can get detection, a reasonably good chance of detecting those changes within 1 to 2 years. And so this is a case of rejecting their quarterly sampling is good enough and having a good argument and an easy way to characterize that no, this is what's needed. This is the sampling frequency that's needed to have consent, have compliance monitoring that is not just a burden, but actually proves value. So you probably have seen this slide. What should we expect? Well, by and large, our national monitoring networks, our state of environment networks are not well suited to detecting change. And that's because they were mostly built to characterize the resource. It's not their fundamental job. This is from a paper, which is no longer in submission. It was accepted about 3 days ago, so that's exciting. And what we said is if we assume that every well in the country went down to 2.4 milligrams a liter in 30 years, it would still take us 30 to 50 years before we'd see that change in more than half of the wells at our sort of current quarterly sampling frequency. And that's not to despair. That's not saying that these networks are pointless or provide no value. It's just that they're not particularly good to this specific question. And even though you're all muted, I can hear you saying, but we've seen changes in the past. We've seen these big concentration changes. And we know that things are increasing. So why can't we see the reductions? And it's really just because we break things fast and we fix them slow. So, you know, a 20% reduction in 10 years is a lot for landowners. But, you know, in the scheme of things, it's quite small relative to the, what's that, 400% increase in the last 30 years. And so that's why that's why it's harder for us to detect reductions or detect these changes than the problematic challenges of the past. One other component to touch on, and this is sort of beyond the scope a little bit, though we will discuss it more as part of the general discussion and worked examples, is the spatial variability. So everything we've been talking about so far is the detection power of a single monitoring well. But of course, the landscape is complex, and it's probably very difficult to impossible to build a statistically robust monitoring network, which accounts for all the spatial variability, right? You've got different land uses. You have cows peeing in slightly different places. You have changes in time. Well, this farmer did winter grazing this year, but next year he didn't because he didn't need to or something. Like there's lots of changes. And so when we're looking at change detection, we need to really aim for targeted monitoring. So with that, this is a slimmed down version of the network design process that was published as part of the Our Land and Water work. And this is a great way to think through what we have. So first we have to define the plans and scenarios, develop a conceptual model of the area, understand our knowledge gaps. Do we need to get some age distribution data? Do we need to sample in different places? Do we need to think about what the spatial variability of those land uses are? Integrate analysis of both surface water and groundwater sites for detection power, and then find the priority sites, the ones where we can actually detect these changes. If we need to, let's identify some new monitoring points, and then let's do some cost-benefit analysis. Are we sampling frequently enough to see something? If not, is it worth sampling at that point if we know we're never going to see anything, just to say that we're doing it? Would that money be better spent sampling in another location or sampling more frequently at another site? So that's our initial design process. And then importantly, we need to review that network again and again and again, because as we collect more data, we understand our systems better, and the detection power might have changed and our requirements might have changed. And so that's why we said after 1 year, 3 years, 5 years, as you're building up your understanding about these networks or new sites, let's review the detection power. So with that, we're going to wrap up. I had a conclusion slide. It seems to have disappeared. Big picture conclusions I wanted to mention is that, one, this is an important, detection power is important. It can help us with large plan to get good plan change monitoring. It can help us define consent conditions and to provide a good piece of evidence to convince stakeholders and consent holders that a certain sampling frequency is necessary. And then our lag is an integral component of this. And if you don't know the age distribution of the water you're sampling, you don't know when you're sampling. And that's a really challenging position to be in. So with that, we can take a time now. And if you have questions, please pop them in the Q&A. And we can answer what we have, and then we'll take a bit of a break, and then we can move into our discussion rooms.
So how long were you taking a break for, Matt? Till 11?
Yes, but right now, so questions for a little bit longer, and then And then, yeah, we'll take a break until 10:10. I believe 11 is an hour later than you wanted. So
Yeah, sorry, my bad. So we haven't got any questions coming through yet. Matt, there were a couple of slides that you went through relatively quickly, and I wonder we might want to spend a couple of minutes while people are thinking of questions, kind of going back through those. Again, can you skip back? I think it was when we were into the relatively early concepts of noise, and yeah, keep going on. Yeah, and possibly the counterfactual as well. Keep going back.
back.
Yeah, back. Yeah, so here, no, on that one there, I think yeah, just explain these up and down arrows, because I don't think you touched on those when you went through it the first time.
Yeah, and it's probably better to touch on them now. So the idea is that what happens what happens to the detection power at a site if this value increases? So, changes in your question or your statistical test, it's complex, it's site specific, can't really comment. As the noise at your site goes up, your detection power goes down. You're not able to see it as well. What changes in the future pathway, what's going to happen? It can be complex, but generally the bigger the change, the easier it is to detect. And the bigger the difference between those two scenarios in that counterfactual space, the easier it is to detect something. And then as your sampling frequency goes up and as your sampling duration goes up, your detection power will increase. Yeah, so we do have a question in here from Luke. When you're adding noise to your model, are you adding it as Gaussian autoregressive noise? To that, it's a simple approach. So here we're just adding random noise to the data. The idea is that means that we are oversampling noise, and so our detection power will aim for a type 2 error rather than a type 1 error, which is what we want. We want the detection power to say, yeah, no, it's not good enough, we need to sample more, rather than to wait to sample for 10 years, lose that time, never be able to get it back, and be in a position of, oh, well, we thought that was going to be enough, but no. So, and the second part of the question is, I understand that to use this method, we need to have a model of our source concentration and then the residence time of that contaminant. So in this case, we're focused mostly on a conservative tracer. But if I go back to this approach here, we don't actually need to know what's happening in our source. We have to model what's happening in our source. And this is a model of that. This very simple source concentration model is a model that allows us to do it. So it's not like you need to use a complex three-dimensional transient groundwater model that's gone through uncertainty analysis and costs, thousands and thousands of dollars. You just need to have something to say, this is where we think things are going.
Mac, before you move on to the next question, I think your cell one example was quite useful for exploring what it means when you don't know what the mean residence time is, because you can then fit a range of possible mean residence time examples through the data and then say, yeah, that one, where could we end up on that basis? So you can still learn something useful. It might be very unconstrained. You might have a very wide range of answers, or perhaps you don't, depending on what your measured data is looking like.
Yeah, I agree with that statement. There is value because detection power analysis and this stuff is actually relatively fast and easy to run. There is a lot of value in just throwing lots of different possibilities out there and seeing what happens, to understand what those levers are and where things are on the edge, to move from that strictly quantitative to a pseudo-quantitative or qualitative approach. So in this case, there's a lot of variability, and our ability to detect changes and where concentrations might go varies dramatically with mean residence time. So that's a very good candidate for spending the money and getting a good age sample, or a set of age samples. Spring-fed streams are obviously more complex because your age distributions can vary with flow. But All right, Manus asks a question. How do you take the climate change impacts into your detection power? And to expand, is the detection power tool able to proportionate the effects of climate change on increases in concentration contamination over time? So yes and no. In terms of how do you take the effects of climate change? So those effects are twofold. One, you have the changes in your pathway, and so that it's however you're modeling your pathway. Would you expect concentrations to increase? Would you expect concentrations to decrease? The other thing is, of course, climate change could increase the noise at our receptor because we get more intense weather events. And that would be about tweaking the noise estimate that you use for these detection power calculations. So it doesn't implicitly take it into account, but rather it's something that you as a practitioner can use to do this. And that's the value of these tooling, is that you're not stuck to the assumptions that a simple set of assumptions. You can make this as complex as you need to for your given site. Paul Schulz, can you use this methodology to build a range of lookup tables to help answer what detection power might be required for a standard range of consent questions, for example? I would say, Paul, it's tricky. I think it's probably more efficient to actually look at it on a site-by-site basis, because the amount of uncertainty, sort of the dimensionality of the problem can be really high, right? You've got sampling frequency, you've got sampling duration, you've got different noises, you've got different age estimates, you have different source concentrations. And so moving to lookup tables, I think, is, in this instance, probably a case of being a little too simple, would be my comment. I don't know if you have any comments on that, Seb, you want to add.
Yeah, no, I think you're right. There's a lot of variables in there, so you'd end up running a lot of simulations to try and figure out the answer to that. And it might be quicker to do it on a site-by-site basis. But I suppose if I can see where you're coming from with that question, Paul, because a lot of times you'll have people reviewing consents that don't have either the time or the capability to go and do this analysis. So that might be something worth looking into a little bit more, Matt. I can see where you're coming from with that.
Yeah, it's a tricky game. We tried to make some lookup tables for during the our Land and Water project, and it really just became a runtime limitation and the table size limitation. As soon as we added lag or mean residence time in any way, it just, the dimensionality exploded, and it became very computationally expensive and very big, and not really a great option there. So Lisa asked a question here. What assumptions are you making about the change that you are trying to detect? Is it instant, incremental, smooth, etc.? Yeah, thanks, Lisa. That's a really useful point. So two parts. So that comes into two different parts. One is the question that you're asking, and two is the pathway that you're developing. So you can develop whatever pathway you want. So if I go to the consent example, sorry for flipping through quickly, but this is kind of a big slide deck. So in this case, right, it's sort of gradual, but there's some weird steps and some changes. So you can make things as complex or as sharp, et cetera, as you want it to. And then, of course, there's the question that you're answering, or you're asking. So in a slope detection power, when you're looking for a reduction, either with a multi-part Mankendal or with a Mankendal or something like that, then that's obviously looking for a smoother reduction. A counterfactual approach will look for those differences. You can also use something like a Pettit test to look for step changes in the data. Though often even step changes in the source will produce sort of more smooth changes in the receptor because of the effects of lag. But the capability in the tooling, which we'll talk about later, allows people to kind of plug in whatever they need in that space. Roland asked, Matt, how sensitive is your analysis to the choice of exponential piston flow models? Are you confident that an EPM suits your stream flow dynamics? Yeah, Roland, that's a great question and a good comment. In cases, yes. In other cases, no. In the spring-fed streams, it's obviously more complex. I'm aware of your work partitioning flows, and that's quite useful. The examples we gave here are kind of a first pass, a simple approach, but the tooling and the methodology means that you can go through all of your partitioning work and then use that to define your forward concentration pathways in order to sample things appropriately. So there's a lot of variability within that. We could either take a few more questions or we could pause now. Yeah, we probably have about 5 more minutes if we want to talk through anything else. Is there anything else you think I missed or went too quickly through, Zeb?
It's kind of hard to tell how everyone's kind of feeling about it, but there's no more questions coming through. I mean, I guess the purpose of the group assignment is to kind of get people thinking about this stuff in a more applied way, which will hopefully kind of flush out any more questions or things that people have maybe not fully understood as we kind of gone through it relatively quickly. So there is kind of an opportunity after that group assignment to come back and do a bit more kind of Q&A and dig through the slides and so on as you break away in groups and talk through the material between you and how you might use it in your day-to-day practice.
Yep. Okay, with that then I would say we can move to a break. We'll reconvene at 10:10, so in about 10 minutes.
We have one more question.
Oh, got one more question. All right, well, we'll answer that first. So Peter Hancock asked, if I'm understanding right, you're saying water aging variable across seasons is critical to understanding that lag. Any further commentary around that, i.e. age being an average, so it's likely to be a range spread of lags that contribute to that? Yeah, so there's a couple of points there. One, I think the most important thing is to move away from an idea of age as in the water is the mean residence time, that when you sample a well and you have a mean residence time of 12, we can't just assume that all that water is 12 years old because there is those range of ages. Variability in age over time is a challenge. There's not a lot of great data to support those changes. I think Uwe's got some data he wants to publish someday about this. Generally speaking, in groundwater situations, those age distributions remain relatively consistent unless there's a big change. So, the advent of pumping in Christchurch, something like that. But yeah, that is definitely an area of active research that would be good to get more information on. Hopefully that answers that question, Peter.
Matt, it's in the report that we put out that's linked in this in the meeting agenda, but the Tehiriri catchment work we did was quite interesting in that it had a kind of like a young mean residence time of like 1 or 2 years, maybe kind of 2 years on average, but we did the analysis for detection power with and without lag. We showed that you got a really significant change in your detection power once you accounted for lag. So if you didn't account for lag over a 10-year sampling period, there was quite a high chance that you'd have a statistical error when you were interpreting the results of that, i.e. you might be saying that no change was happening, there was no reduction due to mitigations, even though there was something going on. So yes, it was a bit of a surprise within kind of thinking with a 2-year lag, you think, okay, that works for its system in a few years, and if you're monitoring over 10 years, then yeah, no problem there, but that wasn't the case at all due to that distribution of ages that we'd used, which was admittedly based on an EPM like Roland flagged, but still it is important even for pretty young lag systems, unless you're talking about a kind of a 20-year sampling duration, in which case it kind of fades away into the background. Yeah, exactly. And it's usually, there's a weighing up of things here, right? Either you can say, oh, we'll just see what happens in 20 years, and it's or in 20, 30, 50 years, depending on, the age of your groundwater, and detection power becomes less relevant. But I don't know very many people who are happy to wait, say like, okay, well, we put millions into making these reductions. We'll see if it worked in 50 years. That's a hard position to stand on. Also, the
I should comment in the spring-fed streams or in streams generally, right? We know that nitrate is largely groundwater derived and base flow derived. So the issue, you can have a age distribution change with flow as you have more or less of those of your fast flow or your surface water flow. And so age in surface water bodies is a little bit more complex. But certainly understanding base flow and the work that you've done, Roland, for instance, is useful in that space.